Okay, we're starting in on chapter 1 in your book, and it's entitled Measurements. So, first thing your book makes the distinction is they want to make sure you know what the word description is, because description is going to lead to your understanding of the environment. Description is basically when you're going out to take measurements. So the descriptive phase is basically the data collection phase. And in that data collection phase, you want to understand what exactly you're trying to collect so you can do accurate measurements. And measurements have been around for a long time. We use measurements in our daily lives, whether we're cooking, whether we're driving, whether we're watching the weather forecasts. There is a question to consider, and that question is, can you measure everything with certainty? And the answer to that is no, because as objects get farther away, it's hard to measure them with certainty. Like if you're going to try to measure the distance to a planet or the distance to a star, those measurements become a little more uncertain than if you're going to measure the distance to the grocery store. Now, one thing we want to clarify is what we're actually going to be studying this semester. We're studying physical science. So physical science composes physics, chemistry, geology, meteorology, and astronomy. Well, this class being SCIE 101, we concentrate on physics and astronomy. If you take SCIE 102, then you will deal with chemistry and geology. So this is a nice flow chart that shows you how you have the main sciences and how they're broken up into social and natural. We're not going to talk about social sciences. We're going to concentrate, like I just said, on physical sciences. And you can see how they're broken up and how they flow together. Earth and space science is actually a subset of meteorology, and we briefly go into a little bit about the atmospheric conditions and atmospheric measurements when you get into SCIE 102. So we have to be able to measure things to investigate, okay? And so we consider measurements to be the basis of scientific research and investigation. Now, some of you might be familiar with the scientific method from previous courses or from high school. The scientific method is what gives us general methods for observations, rules for reasoning, and making predictions. We break it up into different steps, first being our observation and measurement phase. You're gathering data in this phase. And then from all that data that you've gathered, then you can move to the hypothesis phase where you're coming up with a tentative answer, basically an educated guess. After you've come up with this educated guess, then you're going to do some experimentation to see if you can prove that hypothesis. If you can't prove it, then you have to modify it or just outright reject it. After you've come up with your hypothesis, again, more testing has got to be done to tell whether you can accept it, confirm it. And the important thing to note in this testing has to be reproducible. It does no good if you're the only one that can reproduce your data set, okay, or reproduce the results from the data set, I should say. So other researchers have to be able to reproduce it. Once that happens, then we can move on to the theory phase, and that's when we've tested that explanation, we've accepted that hypothesis, so we're able to move on to that theory phase. And then following the theory phase is we have the formation of the law, where you're going to give a very concise statement of that fundamental relationship, That statement could be an equation, it could be a sentence. Sentence such as the law of conservation of mass, that is stated right there, that's considered to be a law. So, other thing to note is that you're simply stating the findings. You're not explaining the behavior. And you can see in this picture how the different steps are broken up and how they flow from top to bottom. So, we're going to be dealing with a lot of different units this semester because basically we're looking at physics for the first part of the course. And so whenever you're solving a problem, you're always going to have a magnitude, how much, and then you're going to have the units to tell you how much of what. Now, the fundamental quantities are going to be those of length, mass, and time. When we get to look at force and motion, we're only going to require 3 of those quantities. A standard unit is something that is fixed and reproducible, so you can take accurate measurements. So if I'm measuring it, how many hours, how many seconds, those are standard units. 2 major systems of units are the English or the British and the metric. So we're used to the English or the British system in the United States. We're used to inches and feet and pounds, whereas the rest of the world have adopted the metric system, so kilograms, grams, meters, kilometers. Now, interesting enough, we quote-unquote officially adopted the metric system back in 1893, but we've never implemented. So, if you're looking at length, what you're basically talking about is you're measuring space in any direction. When you're looking at space, you're dealing with 3 dimensions, length, width, and height. So in the metric system, it's going to be our meter. In the British or English, it's going to be the foot. Now that foot is referenced to our human foot, whereas the meter was originally defined as 1/10,000th of a distance from the equator to the North Pole. And that can be seen in this figure right here, going from equator to North Pole. But then we started to refine it a little bit as we got more information. And now we know and we define the meter to be the distance that light travels in a vacuum over the time. So what about mass? Well, mass is how much matter an object contains. Now, mass is always constant. So what I mean by that statement is if you take the mass of yourself on the Earth and then travel to the moon, you're going to have the same mass no matter where you're located because it's a constant throughout the universe. In the metric system, we use the kilogram, which was originally defined as the amount of water in a 0.1 meter cube, and it's referenced to a cylinder in Paris, that you can see this cylinder in Paris in this diagram. Now, in the English or the British system, the slug unit is rarely used. What we typically use is the pound. But interesting enough, the pound is not a unit of mass, but is a unit of weight. The reason it's a unit of weight because it has to do with the gravitational attraction in addition to the mass. So, depending on where you're going to be taking your weight, it's going to fluctuate. As shown in this picture, if I take my weight on the Earth compared to my weight on the moon, I get 2 different values. Time is considered to be the continuous forward flow of events. Time only flows in the forward direction. It doesn't flow in the backward direction. And the standard unit for both English as well as metric is the seconds. Initially, we defined it as a amount of the solar day, 1/86,400th, but now we base it on the vibration of the cesium-133 atom, which is our atomic clock. And you can see that in this slide. You can see originally is our solar day, and now we use the radiation frequency of the cesium-133 atom. Sometimes you might see the metric system referred to as MKS, and that just simply means meter, kilogram, and a second. The reason why it's been adopted, it's easier to use than the English or the British system because it's on a base 10 system. Okay, you might see it also called the international system, and it basically contains 7 base units. The units are shown here, so you have meter, kilogram, second, amp, Kelvin, mole, and candela, depending on what you're measuring. The base 10, you can see in this slide, I give you a comparison between the English as well as the metric examples, and notice how easy the metric is. A kilometer is 1,000 meters. Whereas look at the English, a mile is 5,280 feet. It's a lot easier to calculate in your head when you're dealing with the base 10 as opposed to that English system. These are some commonly used prefixes: mega, kilo, centi, and milli. So these are prefixes. They can go in front of any of the units. You can have a kilogram, a kilometer. You can have a centimeter, a centigram. Okay. In terms of volume, we use a liter, and it is just the volume of liquid in a 0.1 meter cube. So, liter of pure liquid water has a mass of about 1 kilogram or 1,000 grams. So you can see a liter is about 1,000 milliliters, and so forth. You can read on the slide to get a little more information. And notice the comparison between a liter and a quart. So a liter is a little more than a quart. And then the kilogram is the amount of water in a 0.10 meter cube. Okay, and you can see our cube here and how a kilogram relates. We also might refer to a metric ton, which is the mass of a cubic meter. Remember, a meter is 100 centimeters. So most of these factors are found on your conversion sheet that can be found on Canvas. And when you take your exam, you are allowed to print out that conversion sheet and have with you, as well as the formula sheet. So when you scan your environment, you will make a scan of those things. So I know when you eyes glance down what you're actually looking at. Okay. The next thing we want to briefly talk about before we end part 1 is conversion. And on this slide talks about how, it's hard to make measurements using only the 7 fundamental units. You're going to have to combine the units in multiples. The area is the square of the length, meter square. Speed is going to be the distance over time, meters per second. So you can see how we can combine them. One example of that combination is density. Density, we use this little funny looking P, which is rho, and it's mass per unit volume. So when we measure density, we're measuring how compact something is. Notice the typical units: grams per cubic centimeters or kilograms per cubic meter. When we get to geology, if you take SCIE 102, you'll be familiar with this measurement, which is the average density of the Earth, 5.5 grams per cubic centimeters. Now that's for solids. What about a liquid? How do we determine a liquid density? Well, we use a hydrometer for that, and that is basically just a weighted glass bulb. The higher it floats, the greater the density of the liquid. You can see a comparison between pure water and seawater. Seawater is just a slight bit denser than pure water. And here's showing you your hydrometer. And like I said, the denser the liquid is, the higher that hydrometer will float. Another thing when you're dealing with units is to remember the combination terms. And you will learn those because as you're working problems, you have to make sure you have the right units to get that combination. So for instance, a Newton is a kilogram meter per second squared. I can't have a Newton unless I have a kilogram meter per second squared. A joule is a kilogram times a meter squared over a second squared. I can't have a joule unless I have that. Same thing with a watt. Okay, we're going to stop part 1 right now, and we will pick up with part 2. Having a little trouble ending this PowerPoint.